Okay, chemistry 111, last class. We stopped somewhere around here. We were talking about what isoelectronic species are, and that's a definition that you certainly need to know for your next exam. Isoelectronic just means atoms that have the same number of electrons. Not the same number of protons, but the same number of electrons, and thus they're going to have the same ground state electron configuration. Now, if you look at elements on the periodic table, you know that if you have the neutral form of any one of those elements, that the atomic number is going to be equal to the number of electrons. But we know that it's not the number of electrons that governs the identity of an element or an ion, whether it be a cation or anion, but the identity of an element is governed by the number of protons. And so we can have all of these different species, just like we have here, which all have different numbers of protons, but they all have the same electron configuration, and they all have the same number of electrons. For example, if we look at a sodium ion, a sodium cation, well, sodium is in group 1A. It has an identity crisis, sodium, right? It wants to lose one electron so that it can be isoelectronic with neon, which is a noble gas. And so we see that its shorthand electron configuration would simply be neon. If we look over at aluminum, which is in the same period, you see that if aluminum loses 1, 2, 3 electrons, it will have 10 electrons, which renders it isoelectronic with neon. Same thing for fluorine. If fluorine gains 1 electron and becomes fluoride, it becomes isoelectronic with neon. We can do the same exercise for oxygen, which becomes an oxide, gains 2 electrons, becomes isoelectronic with neon, and the same thing for a nitride. And so all of these ions are isoelectronic with neon. They all have 10 electrons. They all have different numbers of protons, but they all have the same number of electrons. And so again, you need to know the definition of what isoelectronic is, and it's going to come up more throughout the lecture this evening. So if we take a look at the electron configurations of cations of transition metals, remember that metals tend to lose electrons, okay? Metals tend to lose electrons. It's only nonmetals that tend to gain electrons. If you go back to the last slide, what were the elements that gained electrons? Nitrogen, oxygen, fluorine to form a nitride, an oxide, or a fluoride, respectively. And so, again, metals like to lose electrons. However, when we form a cation from a transition metal, we don't do that identity crisis thing. We're not going to just simply seek to lose a certain amount of number of electrons that will render the transition metal isoelectronic with a noble gas. It's not that simple, okay? And so you actually kind of have to memorize what some of the possible ions are for the transition metals. For example, if we take a look at the electron configuration of iron, you see the iron is element number 26 in the periodic table. So its shorthand electron configuration is argon, which covers the first 18 electrons, right? Because argon has 18 electrons, plus 4s2, and then 3d6. But iron can form 2 possible cations. It can form an iron 2 plus cation or an iron 3 plus cation. Say, for example, if you had FeCl2, you can also have FeCl3, right? Those are iron 2 chloride and iron 3 chloride, respectively. Anyhow, when we remove electrons to make these cations, it might be a knee-jerk reaction to say, well, when I was building the electron configuration of iron and I followed the periodic table, the 4s2 electrons went in first, and then the 3d6 electrons went in second. So you might think, well, if I need to remove 2 electrons to make a 2 plus cation, I'll just take them from here. However, we don't do that, okay? We actually take them from the s orbital first. So if we make a 2 plus cation, we would remove both of the electrons from the s orbital. And if we made a 3 plus cation, we remove, the 2 electrons from the s orbital and 1 electron from the d orbital. And I have that rule summarized right here. It says when you form a cation from a transition metal, the electrons are always removed first from the s orbital, okay, the ns orbital, and n is the period number. And then you start removing them from the n-1 d orbital. So we see if we have manganese, oops, there we go, manganese, which is element number 25. So we have the core electrons here. We have 4s2, 3d5. If we want to make a 2+ cation for our manganese, we would remove the electrons from here. There's a name for this rule, which is not in our textbook, so I'm not going to write it down. But sometimes you hear this called the first in, first out rule. What that means is, again, if you're building up the electron configuration of an element like manganese, you'd have argon, which is the core electrons. The first ones in from the next period would be the 4s2, and then you would do the 3d5. So the first ones in, again, were the s electrons, but they're also the first ones that are removed. Okay, so the first in, first out rule. And you could find that, if you were to peruse the internet. Anyhow, there we go. Some interesting exceptions that I'd mentioned last class are things like chromium and copper. So if you look at the electron configuration of chromium, and again, I went over this last class, the electron configuration of chromium, you might think that it would be argon, and then chromium is element number 24, so you might think it's 4s2, 3d, 1, 2, 3, 4, 3d4, like that. But in fact, that is not the electron configuration of chromium. The correct electron configuration of chromium is actually 4s1, 3d5. That is an exception. Okay, and the reason why this is the acceptable electron configuration for chromium is because there's a greater stability when we have the s orbital and the d orbital both half filled. Okay, they're both half filled. Whereas in the first one, I only had one of them completely filled. The same thing, or excuse me, we see the same thing with copper. If you look at copper on the periodic table, it's element number 29. So you might think, okay, well, I have argon, and then I'm going to have 4s2, 3d9. But in fact, that is not the electron configuration of copper. When you look it up, you should see something that says 4s1, 3d10. And again, the reason why is because here we had one completely filled orbital and one not filled orbital, and it's also not half filled. But now we have one orbital that's half full and one that's completely full. And so this is a more stable electron configuration. Something that's kind of funny is if you look at the periodic table and you go down these groups, down the group that has chromium in it and down the group that has copper in it, you see the same rule applies for molybdenum, which is just below chromium. You see the same rule applies for silver, which is just below copper. You also see that the same rule applies for gold. Okay, so all of these elements follow this rule. But once we get to tungsten, tungsten doesn't follow that rule. So it's only followed by the first two. And the reason why is beyond the scope of our course. And you might be wondering, do I have to know those exceptions? I would say yes, absolutely, because the ACS loves to ask these kinds of exceptions. Anyhow, let's move on and let's talk about the concept of effective nuclear charge. I was teaching a general chemistry class a couple of years ago, and I was teaching from a different textbook, and there was a very bold statement in that textbook. And the statement was this, okay? The statement was all periodic trends, and we're going to look at several of them, whether they're ionization energy, electron affinity, also, atomic radius, what else? Electronegativity. All of these periodic trends can all be rationalized or explained using effective nuclear charge. And so that's just my preamble to tell you that effective nuclear charge is a very important concept in general chemistry. And it helps us to understand some trends in periodicity that might not be intuitive. Let me tell you what effective nuclear charge is. It's pretty well described by the title, effective nuclear charge. It's the amount of positive charge in the nucleus that's felt by an electron, right? Because a nucleus has a positive charge, doesn't it, right? We know that a nucleus of an atom is protons and neutrons. Of course, in hydrogen, we only have one proton. We don't have a neutron, but usually we have protons and neutrons. But overall, the charge of a nucleus is positive. So if we have that positively charged nucleus and we have an electron, if we have an electron in an orbit, going around this, and this is just a simplified model. I'm kind of borrowing from the Bohr model here, but there's an attractive force, right? We have the negative charge on the electron and we have the positive charge here. There's some kind of attractive force. Well, how much of that positive force of that nucleus is the electron feeling. And there's a very simple calculation we can do to give us an estimate on effective nuclear charge. It's not the exact numbers, but it's pretty darn close, and it will be what's the word, appropriate for our discussion. So the formula is this, is that effective nuclear charge is equal to Z subtract sigma. Z is the number of inner or core electrons. Remember when we did those shorthand electron configurations and we had the noble gas configuration before? Yeah, well, the noble gas configuration makes up all of the core electrons, okay? And sigma simply means the total number of electrons, okay? So sigma is the total number of electrons. There we go. So I think I have it wrong. Yeah, sorry, my mistake. So sigma is, I was like, that's not right. Sigma is the number of core electrons. So core electrons, this is the sigma right here. And Z is the total number of electrons, okay? So this is what I thought this was a hyphen, but this is actually a subtract. So if we want to calculate effective nuclear charge, we take the total number of electrons, and then we subtract the number of inner or core electrons. That's the sigma. Sorry, my mistake. Anyhow, and if you're like, well, what do you mean by that? Let me show you what I mean. Let's say we take a look at sodium and we write out a shorthand electron configuration for sodium. The shorthand electron configuration for sodium would be neon 3s1. The shorthand electron configuration for magnesium would be neon 3s2. The shorthand electron configuration for aluminum would be neon, you can see where I'm going here, 3s1, 3p1. The shorthand for silicon, I don't know why I'm writing silicon there, is neon 3s2, 3p2. So how many core electrons do we have? Neon has 10 electrons, right? So that means the number of core electrons, so we'll put neon is always equal to 10 electrons, and that's equal to our sigma. So you can see that that doesn't change. But the total number of electrons is increasing, right? Here we have 10 plus 1, that's 11. Here we have 10 plus 2, that's 12. Then we have 13 and 14, respectively. So if we just do some quick math, if you take Z minus sigma as being your effective nuclear charge, you have 11 minus 10 gives you 1, 12 minus 10 gives you 2, 3, and 4. Okay, so what happens as effective nuclear charge increases? Again, effective nuclear charge is increasing. What happens to the atomic radius? This is atomic radius. That the atomic radius is decreasing. That's kind of interesting. I think it's counterintuitive. At least it was the first time I saw it. Because what's happening here? Now, as we go across the period from sodium to magnesium to aluminum to silicon, what's happening to the number of protons in the nucleus? It's increasing, isn't it? Right, so the positive charge on the nucleus is increasing as we go across the periodic table. Now, the way I thought about this the first time I heard it is I thought, well, come on. If you're going from sodium to magnesium to aluminum to silicon, shouldn't the radius get bigger? Because you're adding matter. Electrons are matter, protons are matter, neutrons are matter. They all take up space. So if something takes up space and I have more of them, shouldn't it take up more space? Not so fast. Remember, we're increasing the total number of protons in the nucleus. Therefore, the positive charge is increasing as we go across the period. But the number of electrons in the core, the number of electrons in the core that are blocking the valence electrons or the outer electrons stays the same. And so less of the effect of the core or the nucleus, the positively charged nucleus, is going to be felt by those outer electrons, right? It might be easier to look at it if we go to a periodic table. So let me back up. I had a periodic table a couple of slides ago. Where was it? Right here, okay? Again, we're going from sodium to magnesium to aluminum to all the way across here. And what we see is that atomic size is decreasing. We always have the same number of core electrons. once I get here, I'm going from n is equal to 1 to 2 to 3. So I'm adding electrons to the highest principal quantum shell, which is they're farther away, right? I'm adding a 3s1, a 3s2, a 3p, so on and so forth. But the electrons that are inside, the core electrons that are blocking that charge, the number doesn't change. It's always 10. So as the nucleus gets more and more positively charged as we go across the period, the valence electrons are going to feel more and more of that effect because there's the same number of electrons blocking the positive charge. And that's what effective nuclear charge is. It's the effect that the nucleus has on the valence or the outermost electrons. So there we go. So if we think about electron configuration and we try to relate it to periodic properties, we see that there's some kind of attraction between electrons, which are negative, and protons, which are positive. It's nothing bad there, okay? In a multi-electron atom, so anything that's not hydrogen, the electrons are not going to experience all of the attractive force of the nucleus, right? The attractive force experienced by an electron in an atom, we call that the effective nuclear charge. Let me explain it to you another way. Okay, effective nuclear charge is a really important concept, so I want to make sure that you follow along with me here. Let's talk about lithium for a second. Lithium is the third element in the periodic table. It has 3 protons in the nucleus. So I'll put 3 protons, 1, 2, 3 protons in the nucleus of a lithium. Well, I've got a 1s orbital, and I've also got a 2s orbital, right? This is the 1s, this is the 2s, right? 2s is a higher principal quantum number, and therefore it should be bigger. In the 2s orbital, I've got 2 electrons, don't I? I've got an electron here, which is negative, and I've got an electron here, let's say. I also have 1 electron in the 2s orbital because the electron configuration of lithium is 1s2, 2s1, so I've got 1 here. All right, so that means that this valence electron, right, that's the outermost electron, it's not going to feel all of the positive charge of the nucleus, is it? Because it's got these 2 guys that are acting as guards. Let me use a different color highlighter. These 2 are blocking them, okay? So those 2 are blocking. So it's 2 on 1, right? They're doing a pretty good job of shielding or blocking the positive charge from that valence electrons. But then what happens when I go over to beryllium? Well, if I draw the nucleus of a beryllium, beryllium is the atom that comes after lithium. I've got 1, 2, 3, 4 protons in my nucleus. I still have the 1s orbital, and I still have the 2s orbital. Okay, now here's where it starts to really make sense. I've got 2 electrons in the 1s, but now I've got 2 electrons in the 2s. So now instead of being 2 on 1, it's 2 on 2. Okay, hopefully you're following me here. That now I have even more positive charge in my nucleus. And for this guy here, how much of the effect of the nucleus, which is even more positively charged, is he going to feel? It's going to feel more because now you've got less electrons blocking that positive charge per valence electron than you did over here. Right? Think about it again. I mean, I can keep re-explaining it over and over. This electron is blocked by 2 electrons with 3 protons in the nucleus. But these valence electrons are only blocked by 2 electrons total, and I've even got more nuclear charge, and therefore the effective nuclear charge, right, ZEF for beryllium is going to be greater than the effective nuclear charge for lithium. And that is why a beryllium atom is actually smaller than a lithium. I know it's not on my slide here, but it is. Give me a thumbs up if you just follow me on the concept. I know I spent a lot of time on it, but it's such an important concept, and I don't think it's intuitive. Some things we look at in chemistry are intuitive, no doubt. Other things, not as much, right? If it was easy, anybody off the street could do it. Okay, so effective nuclear charge. I have a few more slides, I think, about effective nuclear charge. Okay, put another way, you've got an electron in an atom. It's got an attraction to the nucleus, but it's going to be repelled by other electrons. And so those inner electrons, those core electrons, are going to reduce the attractive force of the nucleus, and we call that shielding. So that's the property of shielding. To calculate ZF another way, we can call that sigma, sometimes we call it the shielding constant, okay? So we have the effective nuclear charge is what the electrons are actually experiencing, right? The Z actual is the total of what they should be experiencing, but of course they don't on account of shielding. Now, what are the trends in the periodic table with respect to effective nuclear charge? As we go from left to right across a period, effective nuclear charge increases. That's pretty intuitive based off of your understanding of this formula that, oops, that wasn't supposed to happen. That effective nuclear charge is equal to Z minus the shielding constant. So total number of electrons subtract the number of core electrons. That's what we looked at on that slide that had lithium and, sodium, magnesium, aluminum, and silicon. When you go down a group, it's not as intuitive, but effective nuclear charge increases. In fact, our book really skates over it. They don't go into a big explanation about it. And even though effective nuclear charge does increase going down a group, you might think, well, if Mr. Dion told me that atomic size decreases when I go from left to right across a period, you know, if effective nuclear charge is increasing going this way, it should decrease too, but in fact it doesn't. Atomic size actually increases going down a group, and it actually makes sense because you're increasing the principal quantum number, right? You're going from n is equal to 1, 2, 3, 4, and so the shells are getting so much bigger that even though the effective nuclear charge increases, the size of the atoms still get bigger. All right, there we go. So effective nuclear charge increases somewhat going down a column, but because we're adding electrons to higher principal quantum or higher shells with higher principal quantum numbers, the atoms are still increasing in size, but based on effective nuclear charge, the size of atoms decreases going across a period. All right, there we go. And if we skip ahead here, you can see, generally speaking, that if we go across a period, and remember, these are trends. These aren't hard and fast rules. These aren't carved in stone. If you go across a period, right, if you go across period 2 or 3, you can see that generally speaking, the size of the atoms decrease, and that's because of effective nuclear charge. Well, let me just back up and cover what's in this slide here, because you might be wondering, how do you measure the size of an atom? It's actually difficult to define the size of an atom because size is 90% of where the electron density is found around the nucleus, right? When we covered atomic orbitals, we discussed that. But when we have a covalent bond between two atoms, whether they're the same or different, we can calculate atomic radius when we have two nuclei of identical atoms that are covalently bound together. So let's say you have a dichlorine molecule, which is Cl2, or let's say you have a bond between two carbons in a molecule. The way that we measure atomic radius is we measure the distance between the two nuclei and these bonds that have identical atoms, and then you just cut it in half, okay? So if you measure the distance between these two nuclei in chlorine, it's 198 picometers, and all you do is divide that in half, and there you go. That's your atomic radius. Same thing with a carbon-carbon bond. And then, now that you've got the atomic radius of a chlorine and the atomic radius of a carbon, then you can define the carbon-chlorine bond length, right? You just would add 99 plus 77, and there you have it. Okay, so that's generally where we get the radius of an atom. That's how we know the size of an atom. And again, I want to take a look at this periodic table here, which shows the size of atoms. So size of atoms increases going down a group. Now, again, I'm repeating myself here, but the reason why is because we're going from n is equal to 1 to 2 to 3 to 4 to 5 to 6, right? That's akin to doing this if I have n is equal to 1 to 2 to 3 to 4, right? So on and so forth. And remember, last class I told you that they increase with the square of the principal quantum number, so they get a lot bigger, right? So again, that's why the size of atoms increase as we go down a group. And you can see that these are trends, right? Trend doesn't mean, if something's a trend, it doesn't mean that everybody in the world is following that, right? There are some rules that all human beings abide by, but When it comes to trends, these are generalizations. So generally speaking, you can see that atomic size increases as we go down a group. But then we said based off of effective nuclear charge, which is equal to atomic number, subtract the shielding constant, sigma, we said that when we go across a period, and you can see the trend here in the second period, you can see the trend here in the third period, you can see the trend here in the fourth period, you can see that generally speaking, atomic size decreases. Now you might notice that if you're astute, you probably notice, you're like, Mr. Dion, I can see that there's some variation in atomic size in the transition metals, but it's not that big. Okay, it's not very big. Well, there's a good reason for that, and that's because when we calculate effective nuclear charge going across the D group, since these are, like, say for example, we start here, we're at 3D, and this is a 4S. Remember, we're calculating Z minus sigma. So as as Z increases, as we go from atomic number for scandium is 21, 22, 23, 24, 25, right? So on and so forth. We also are adding a number to the sigma. So effective nuclear charge isn't increasing when we go across the D block. Generally speaking, it doesn't increase very much, okay? So here it is plotted in a graph. And let's say you were to look at the alkali metals, for example. So the alkali metals are the metals that are found in group 1, okay? You can see that if we go down group 1A, so this is 1A, group 1A, we go from lithium to sodium to potassium to rubidium to cesium, that atomic size increases. You can see the same thing with the noble gases from helium, argon to krypton, xenon, right? They increase there. And the noble gases, that's group 8A. But again, the author took the time to highlight that there's not a whole lot of change in the transition metals. Yeah, there's some variation, and every nuance isn't covered in an introductory chemistry class like this. But again, based off of effective nuclear charge being equal to Z, which is the total number of electrons, or the atomic number, subtract the shielding constant, when we go across the transition elements, right, every time we add one to the number of electrons, we're also adding one to the number of core electrons, because we're adding d electrons, right? Anyhow, well, let's move on from there. And again, if you're wondering, oh boy, how much do I have to have all this memorized? What you have to have memorized is the trend. And you don't even have to memorize it, you just have to understand it. Why the elements increase in size when we go down a period. Why is it that when we go across, why the elements increase in size going down a group, and why they decrease in size going down or going across a period, right? This is a period, this is a period, so on and so forth. And generally speaking, the sizes decrease going down a period. All right. So atomic radius, just a little more information about atomic radius. This is, if you can't see it here, this is just a graph that shows the relationship between atomic radius and effective nuclear charge. I can cover this in about a couple of seconds. All you need to understand is that as effective nuclear charge increases, what happens to atomic radius? Whoop, it drops, okay? Just because the valence shell electrons are going to be pulled in more tightly, because the number of core electrons doesn't change, but the number of protons in the nucleus increases. Nothing more than that. If you're wondering, what kind of question could you ask me about this? Here you go. I gave you a little chunk of the periodic table, and it just asks you, which would you expect to be the largest element? So we've got gallium or arsenic. Could anybody predict which one of these would be the biggest one, the largest element, biggest atomic radius? Yeah, thanks, Anthony. The answer is gallium, right? Because we know that effective nuclear charge increases as we go across a period, and so size decreases. So size decreases going this way. If you want to try calculating effective nuclear charge for gallium, our Z effective Z effective, sorry, I got to remember I'm in the United States here. The Z effective, the atomic number of gallium is 31. It's got how many core electrons? Well, the noble gas that precedes gallium is argon, so it's got 18 core electrons. So 31 minus 18 gives us an effective nuclear charge of roughly 13. If we try the same exercise for arsenic, so for arsenic, our effective nuclear charge is going to be equal to 33, and we still get 18 core electrons, and now we've got 15. And so since the effective nuclear charge of arsenic is higher, it should have a smaller radius, and that's it. It should be a smaller atom. Let's try another one. Now we're on the other side of the periodic table. Now we're looking at mostly metals. Over here are all metals, I guess, except for hydrogen. It says, which atom would you expect to be larger, potassium or magnesium? So let's zoom in. We've got potassium and magnesium. This one's different because they're in different periods, aren't they? Magnesium is in period 3 and potassium is in period 4. Does anybody have an idea which one of these would be larger? And it's not a trick question. There are no trick questions. Yeah, thanks, Anthony. It would be potassium. It's actually quite a bit bigger. Okay, the answer is potassium. And we're not going to calculate principal quantum number here. The rationale is going to be the principal quantum number. It has the highest n, right? N is equal to 4, and the highest n for magnesium is going to be 3. And so since potassium has a higher principal quantum number for its valence electrons, it's going to be significantly larger than magnesium. What they're trying to not trick you on here, but the question that's being asked indirectly here is, even if you were to understand that effective nuclear charge is increasing going across a period, you understand that even though magnesium is further to the right on the periodic table, that in a relationship so close that the principal quantum number would dominate. Here's a beautiful periodic table that shows you the trends in atomic sizes. So down a column, the principal quantum number increases, atomic size increases, not much of a stretch there. Roughly, this is talking about transition metals. When we go across a row or a period, you can see that there's very little variation for the transition metals, and I explained why that is. Okay, there is some variation, and that is beyond the scope of our course. But again, the effective nuclear charge remains pretty much constant, because when we're calculating the effective nuclear charge for a transition metal, we have Z and sigma, and as Z increases, right, so does sigma. There we go. All right. This is just a picture I took from our textbook that shows a covalent radius and a metallic radius, and we'll talk more about covalent bonding and metallic bonding later on in the class. And again, it kind of helps you to rationalize how we define atomic radius. If we have a nucleus here and a nucleus here, an atomic radius is simply 1/2 the distance between two nuclei in adjacent atoms. Okay, so this would be the distance between the two nuclei, and so the radius would be the distance divided by 2, right? And we saw that a couple slides ago. All right, here's another slide, and this just shows main group elements. So the transition metals are left out here deliberately, because it's much easier to see the trend in atomic sizes when you leave the transition metals out, right? You can see we go right from group 2A to 3A. When I was in high school, this is one of my favorite pictures. I always like to look at the size of the elements and, think about them and everything. Anyhow, again, these are trends. Repeat after me, trends. Okay, these are not hard, fast rules. Yes, I know there's some variation. Yes, I know that there's times where, it's reversed, where it doesn't always follow the rules. But generally speaking, we see that atomic size decreases going this way and increases this way. The rationale here would be effective nuclear charge, and the rationale here would be principal quantum number n. There we go. I think that's enough information. Here again, is just a graphical representation of the trends in atomic radii. We have from lithium to fluorine, so this is the second period, so this is n is equal to 2, this is n is equal to 3, this is n is equal to 4, this is n is equal to 5, and then with cesium, this is n is equal to 6. And again, we see that atomic radius decreases going across a period, except for around the transition metals. We see that they don't change nearly as much. All right, well, with all that in mind, let's try another practice problem. It just says, referring to a periodic table, arrange the following atoms in order of increasing atomic radius. I'll just draw a chunk of the periodic table here for you, because we need to arrange phosphorus, silicon, and nitrogen. So I have there's the chunk of the periodic table that we need. So we have phosphorus, silicon, and nitrogen. Could anybody tell me which one of these would be the smallest one, the smallest radius between these three elements? There's one that would be significantly smaller. Yeah, thanks, Branson. Yeah, you're absolutely correct. Nitrogen is going to be significantly smaller, right? Because the principal quantum number for the highest principal quantum number for the second period is going to be n is equal to 2, and then here we have n is equal to 3. So the smallest one will be nitrogen. Could anybody tell me what would be next? What would be the next largest? So after nitrogen, it's going to be phosphorus, right? And then silicon will be the largest, right? Because phosphorus is smaller than silicon because effective nuclear charge increases as we go from left to right across the periodic table. Okay? Again, if you want me to write this down, we'll say here silicon, or maybe I'll phrase it like this. Phosphorus is smaller than silicon due to higher effective nuclear charge, like that. All right. Now, what would happen if we have an anion or a cation? Let's talk about the difference between an atomic radius and an ionic radius. I've gone over this quite a bit, that metals tend to lose electrons and form cations. Non-metals like to gain electrons and become anions. Well, let's start by looking at cations. And we see that the trend is, as we go from, let's say, a lithium element, its pure form, to a lithium cation, you see that the size of the ionic radius is less than that of the atomic radius. And that's the trend we see all across the board. Right? We go from lithium to sodium, potassium, so on and so forth. You see that all of their +1 cations are smaller. Does that make sense? It makes sense to me because the number of protons, let's say you're comparing potassium and a potassium ion, the number of protons remained the same when you lost an electron. When you went from here to here, you get potassium plus an electron. So you lost an electron from the element, but the number of protons stays the same. So it makes sense that now you've got more positive charge per total number of electrons. So they're going to be pulled in, even tighter. The opposite is true when I add electrons. Look what happens here. The trend is the opposite. If I go from fluorine to a fluoride, or chlorine to a chloride, or bromine to a bromide, or iodine to an iodide, you see that the ionic radius is greater than the atomic radius. Why? Because now I'm adding an extra electron. I still have the same number of protons here that I did here. So now that I've got even more electrons up here, they're going to feel overall a little bit less of the positive attractive force of that nucleus pulling them in. Also, on top of that, you're adding electrons to the highest principal quantum number, and they're going to start to repel each other. When they start to repel each other, they need more space. Give me a thumbs up if you follow me on that, or let me know if you have a question about this, because I want to take a look at slide that shows the formation of an ionic compound and talk about it a little more. Okay, again, if you have a question about ionic radii, feel free to stop me at any point. It might not be intuitive. Sometimes, sometimes students find this a little bit more intuitive of a concept. But let's take a look at what happens when we form an ionic compound, right? Fluorine, super strong oxidizing agent. Lithium, really powerful reducing agent. What happens when you put them together? Kaboom, right? You make an ionic compound, right? That's something that you all know by now, that lithium is a metal. It likes to lose electrons. We know that since lithium is in group 1A, it likes to become a +1 cation. That when fluorine, since it's in group 7A, since it's a halogen, it likes to gain 1 electron to become isoelectronic with a noble gas, right? This lithium cation is now isoelectronic with helium, and this fluoride is now isoelectronic with neon in the lithium fluoride compound. So look what happens. When the lithium loses an electron, right, over here, I had 3 protons in the nucleus. Okay, let me draw it really quickly. I had 3 protons in the nucleus, and I had 1, 2, 3 electrons surrounding it. But now I've got 1, 2, 3 protons in the nucleus, and I've only got 2 electrons. So those electrons are going to be pulled in even tighter. Now, I'm not going to draw all 9 protons in the nucleus of the fluorine atom, but hopefully understand that the size of the positive charge here is the exact same as the magnitude of the positive charge there, but now I've got an extra electron, right? So they're just not going to be held as tightly. And the reason that this is so important, the reason why we're spending so much time talking about ionic size, is that the size of an ion is going to govern the type of crystal that's formed when we make an ionic compound. Now, that's something that we're going to look at later: a body-centered cubic crystal, a face-centered cubic crystal, a simple cubic crystal. And then, if that's something you're interested in, you might want to take a look at beforehand. But I digress. You need to understand why cations and anions are smaller and larger, respectively, than their parent atoms. Here is the trend in radii of ions for familiar elements. So you can see that in here we even threw in a smattering of transition metals, didn't we? There's one thing in here that I really want to cover with you before we're done lecture tonight, okay? And that is transition metals that are capable of having more than 1 oxidation number, or capable of having more than 1 charge. I want to let's start by looking at iron 3+ and iron 2+, right? I'm sure you're all perfectly aware by now that iron can form these 2 possible charges. Well, what about the radii of those 2 ions? Hopefully it makes some sense to you that an iron 3+ ion is going to be smaller than an iron 2+ ion, right? An iron 3+ is smaller than iron 2+, right? So larger, smaller. Why? Because the number of protons in the nucleus for both of these is the exact same. They both have 26 protons, don't they? Because they're both element number 26. But what happens when I have an iron 3+ ion? I have 1 less electron, but I still have those 26 protons. Right here I had 26 protons. Here I have 26 protons, but how many electrons do I have here? I've got 23, and here I've got 24. And so these 23 electrons are going to feel a greater attractive force. Give me a thumbs up if that makes some sense to you, so I can move on to the next topic instead of me keeping rambling on about the same old thing. Okay. I just don't want to move on with if somebody's really not following here. Okay, cool. All right, very important concept. And you see the same concept when you look at copper, right? Copper 2 and copper 1. Copper 2 is going to be smaller than copper 1. So notice that the cations, which come from metals, right, are generally smaller than the anions that come from nonmetals. Kind of interesting, huh? And again, as we add more and more negative charge, we have a bigger anion, and as we have more and more positive charge, we have smaller cations. Anyhow, I feel like I've spent quite a bit of time on that. Well, the best way to see if you understand it or not is to always give the old college try, try a question. Indicate, for each of the following pairs, indicate which one of the two species is larger. All right, if I look at nitride and fluoride, so A, just to kind of discuss it here, nitride and fluoride both are isoelectronic with neon. They both have a total of 10 electrons, but how many protons are in the nucleus of each one of these? Nitrogen has 7 protons, and fluorine has 9 protons. Therefore, which one of these do you think is going to be larger? Yeah, absolutely. Thanks, Christina. The answer is nitrogen, right? The nitride, or N3 minus, that's called a nitride. So N3 minus is nitride. Okay, a nitride is going to be way bigger. Okay, much, much bigger. Why? Let's think about it. It's got the same number of electrons as fluoride, but it's got less protons to rain those electrons in, and so the radius is simply going to be bigger. If we look at magnesium 2 plus and calcium 2 plus, well, here they're both isoelectronic with different noble gases. Magnesium is isoelectronic with neon, and calcium 2 plus is isoelectronic with argon. So we can't use that argument again. But they're both 2 plus ions, and they both are alkaline earths. Which one do you think is going to be bigger? Thanks, Christina. Yeah, it's going to be calcium 2 plus, because calcium 2 plus, even though it's lost 2 electrons, the magnesium has lost 2 electrons as well. And so the outer electrons are in a higher principal quantum number. So outer electrons are farther away from the nucleus. So we can put it like this: outer electrons further from nucleus. Good gravy. I can't see what these bonuses. Nucleus. There we go. All right, iron 2 and iron 3. Well, we went over this one a little bit, and we said that iron 3 is going to be smaller, so iron 2 is going to be larger. Okay, there we go. And you can see, hopefully, how easy this kind of material lends itself to me designing a multiple choice question. I mean, nothing could be simpler than for me to come up with a multiple choice question. I just give you a bunch of ions. Which one's the largest? Which one's the smallest? Arrange these in order of size. So not a lot of work involved in that. Anyhow, let's move on and let's talk about the subject of ionization energy. If you're wondering, why are you talking about, sizes of atoms, sizes of ions, effective nuclear charge? Because we're taking a look at the periodic table, right? That's what chapter 8 is all about. It's just looking at the periodic table. And now we're going to go beyond things like molar mass and electron configuration, and we're going to look at trends in the periodic table. So we're learning some new concepts along the way. One of those concepts is ionization energy. You need to know the definition of ionization energy. And let's think about electrons that are in an atom are going to be attracted to the nucleus. So it makes sense that it takes some energy to rip an electron off of an atom, right? If you want to tear an electron away from an atom in order to make a cation, which is what's being represented here. If you take an element, you rip an electron off of it, you form a cation. Well, there's some energy that you're going to have to input to do that, and we call that ionization energy. To add to that, ionization energy is the minimum amount of energy that's required to remove an electron from an element, a gaseous element, in its ground state. So it's got to be an atom in its gaseous state. You're like, what, even metal like iron? Yeah, you have to vaporize it. So that means you'd have to subject it to high temperature and low pressure. But that's neither here nor there. It's a definition that you need to be familiar with. Check out this trend. That ionization energy increases. Let me explain to you what that means. If I take an atom in the gaseous phase and I put in some energy and I rip an electron off of it, I make a cation. Now, what do we know about the size of a cation versus a neutral element? The cation is going to be smaller, and the electrons are going to be held tighter now. So it makes sense that if it's like, okay, well, now I've got something that's positively charged, it's going to hold on to electrons like grim death. So that means if I want to put in the energy to rip off another electron, it's going to take even more energy. Once I've got a doubly charged cation, it takes even more energy to rip off the next electron. So the whole idea is that each successive electron that you pull off or rip off of an atom in the gaseous phase takes more and more energy. The reason why ionization energies are measured in the gaseous phase is because in the gaseous phase, the elements are going to be further apart from one another, and you don't have to worry about or take into account the attractive forces of other elements. It's mentioned quickly in the book. I thought I'd just throw that out there to you. Now, what's really cool about ionization energies is you can look at simply a table with numerical data, namely the ionization energies of elements, and just by looking at the numbers without even knowing the identity of an element, you are able to determine how many valence electrons an element has. What? How would I do that? Let me show you how. This will probably be kind of where we end up, but this is a very cool thing. Let's say we pick an element like, I don't know, let me think here. Let's pick nitrogen, okay? And if we pick nitrogen, now let's make it easier. Let's pick calcium, okay? The last one. I'm trying to think of the easiest example to start with, okay? Let's say we have calcium. Well, I know you guys know where calcium is in the periodic table. It's group 2A, right? It's an alkaline earth. Here we have first, second, third, fourth, fifth, sixth ionization energy. Okay. Well, look at the amount of energy that it takes to remove the first electron from calcium. Okay. So this is the amount of energy in kilojoules per mole. At this point, you'd have a calcium plus ion, right? Well, we know that calcium likes to form calcium 2 plus. So if you remove the second electron, is it going to take more energy? Hell yeah, right? Because now the electrons are held even more tightly. So now we've got a calcium 2 plus, and calcium 2 plus is isoelectronic with argon, isn't it? Right? Now it's got a noble gas configuration. So now if we go to remove another electron, whoa, it goes from 590 to 1145 all the way up to almost 5,000. So we have a big jump, okay? And the reason there's a big jump is because now you're ripping off core electrons, okay? Pulling off core electrons takes a lot of energy to remove core electrons. Let's say you had beryllium, okay? Same rationale. Beryllium is in group 2. Look at the first ionization energy, 900. Then we go up to 1760, right? And then there's a huge jump here. So by looking for those jumps, you can tell how many valence electrons. Where the jump occurs, the electrons before are valence electrons, and the electrons after are core electrons. Okay? Let's say we tried the same thing with carbon. Could somebody tell me how many valence electrons carbon has without looking at this table? Not a trick question. If we just write out the electron configuration for carbon. Thanks, Anthony. You're absolutely right. Carbon is 1s2, 2s2, 2p2. So that means that carbon has a total of 4 valence electrons. Let's see if that makes sense by looking at the ionization energies of carbon. Look, we go from 1,000, double it, a little more, and then look, all of a sudden it skyrockets from 6,000 to 38,000. How many did we do? 1, 2, 3, 4. 4 valence electrons. Okay. So a question that I always ask on every exam, now don't quote me on that, but usually on every exam is I'll give you some ionization energies and just say, how many valence electrons are in this, element? All you have to do is look for the big jump and you say, well, I had 4 ionization energies before the big jump occurred. That means there's 4 valence electrons, and that's it. Here is a graph that shows ionization energy plotted versus atomic number, or the first ionization energy plotted against atomic number. A lot of this will make sense to you, right? It makes sense that as you go down the noble gases from helium to neon to argon to krypton to xenon, so on and so forth, that first of all, within a period, if you go from lithium to neon, for example, that the ionization should enter, the first ionization energy should increase as we go across a period. Why? Because effective nuclear charge increases as we go across a period. right? But when we go down a group, which is what's being done here, the ionization energy decreases because atomic size increases. Something else I'll just point out to you that I think I neglected to say, the ionization energy, you notice that it's always a positive number, right? It's always a positive number. Ionization energy, I'll write it down here. Ionization energy is always endothermic. It always requires some energy being put in. All right. So the noble gases are going to have the highest ionization energies. Their valence shells are completely full. They're totally happy. They don't want to lose electrons. The group 1 elements, you know, they're just spoiling to lose an electron, right? So they can become isoelectronic with a noble gas. All right, and this is the general trend in first ionization energies. And of course, you're responsible for knowing that.